And we're live. Welcome, everybody. I want to welcome you to Maximizing Data Label Operations in High Stakes Industries. I'm Keith McCormick. I'm joined by Alberto Rizzoli here. I'm the Chief Data Science Advisor for CloudFactory, and we provide human-powered data labeling and data processing for AI and automation. Alberto will tell you a bit more about V7 as we go, but they've created a machine learning platform, and they're also a CloudFactory partner. So if you've attended these before, you know that we like to jump right into it, and that's what we're certainly going to do in this case. And then we're going to chat for about 40 minutes. We have a number of topics that we've discussed that we want to include, but we're going to save as much time as possible for questions. It's very often the most fun part of the show. So you can start thinking about those questions now, and in about 40 minutes, we'll start focusing our attention on those. So let's start with the very first topic. And Alberto, you know, this is a topic that I'm particularly curious about. And we've talked about this a number of these interviews this year. There seems to be a growing consensus that, you know, when newly minted data scientists get out of school, and this can include graduate school at elite programs, data labeling, data annotation, human in the loop, all these related topics don't seem to get a lot of classroom attention. And the folks, enter industry not being very familiar with this very important topic. One, is that consistent with your experience, and what do you think is going on?
Yeah, we're kind of being catapulted into a data-centric AI paradigm of AI since basically the deep learning era, since 2013. And I think curricula has taken some time to catch up, as well as technologies and tools like V7 itself, to really change the world from models like we did before we had enormous amounts of training data to use, and before we had GPUs and all the other parallel processing hardware, and moving towards this world in which the data set is one of the more important parts, if not the most important parts, of an AI company's competitive advantage. So there's still a bit of a disconnect between the academic world and what you're taught. Generally, make the most efficient possible network architecture to solve a fixed data set. ImageNet traditionally, now we have a lot more new academic data sets that are a little better, into one that industry tends to take care of, which is we have to solve a problem and we have to build a data set to solve the problem. We're probably going to use the most state-of-the-art architectures for it. How do we label data in a way that we can create the best possible self-driving car, the best possible tumor detecting CT scanner, the best possible insurance claims processing bot? And this is a mind shift that changes both the tools required as well as the mentality of a data scientist from one topic to the other. Nonetheless, we're all standing on the shoulders of academia's kind of giantesque role in deep learning, but it's cool to see that there's this evolution happening.
Yeah, it's interesting. I want to help clarify the time frame a little bit for everybody, because you mentioned a couple of things that are quite interesting there, particularly about the tools, and I hadn't thought about it this way. First, you pointed out, 2012, 2013 is when we all started talking about deep learning. And then if you think about tools like TensorFlow, to actually build the deep learning, maybe we're around just a couple of years more recent than that, 6-7 years or so. When did you start to see the activity in the data annotation platform, like the work that you all do at V7? I mean, that's probably even younger, right?
Yeah, so V7 was founded in 2018, but between that and our launch in 2019 in beta was a lot of development. But the changes started happening in 2015. So other players in the space like Scale have started earlier around that era, and that was kind of the gold rush start for deep learning. After the Krzyzewski paper in 2013, we saw all the major companies start to acquire startups that sometimes had very little, and I shall not make names in regards to this, but they had incredible talent within them, very talented deep learning PhDs that understood, they got the field. And in parallel, tools started to appear to actually make this thing work. So I think the first training data platform experiences started in 2015, and they were generally in the image and text classification side. So very simple stuff, add a tag to an image. Then we started to see bounding box-based tools that kind of the second layer of simplicity, just add 2 points around an object. Today, though, we no longer call them annotation tools because just labeling an image is not where a lot of the value is. It's in creating this training data orchestration, what we now call ML ops, and being able to have the model and the data set sit in the same home, because ultimately they are one and the same. The model is a compressed version of the data set itself. So it's been also cool to see the kind of this new branch of software evolve into pretty much the same storyline that kind of code-based traditional software 1.0 evolution happened in the 90s and early 2000s.
Yeah, no, it's interesting. But when you think about it, if we're about 5 years into this, describing the kind of technologies that you're describing, it's not shocking that academia hasn't caught up in terms of curricula, because the wheels turn pretty slowly there. New programs have to be approved, and the whole 9 yards. I actually have a little bit of experience sitting in on these meetings. So, if we're only 5 or 6 years in, perhaps it's not that surprising that there's a game of catch up, being played. We always do a poll. I think I mentioned this to you, and this time we had a three-way tie, which is a first. We asked, what's the biggest hurdle in your data labeling operations? And folks gave answers: scaling teams, limited subject matter experts to review data, and our data is quite complex. And the one that got fewer votes was only a few percentage points behind hard to pick labeling tools, topic that we were just talking about. So regarding the limited SMEs, that segues right into our next question. And this is something else I've continued to be fascinated with as I've learned more and more about this about a year after joining CloudFactory now. And that's that you can have somebody that becomes a specialist in medical image annotation, somebody like the folks that work with CloudFactory, and they have many months of experience, sometimes more than a year of experience doing that. So there will be certain use cases where that experience becomes more helpful to the task than, let's say, a medical doctor. And this is probably very surprising to folks, but how do you kind of compare and contrast those two different kinds of expertise? The person who has seen hundreds and hundreds of these images over a long period of time, and the kind of training that a medical doctor has.
Yeah. So I want to make a quick correction on the record regarding the role of academia. It isn't quite so that like the catch-up thing is a bad thing. It's mainly that academia is solving the fundamental problems of our field, and industry is kind of piggybacking on top of that and trying to apply it to other stuff. And the two worlds have different focuses. So just for the record, because we're basically all relying on academics to actually build this field. Don't want to actually diminish the.
No. That's a good point. Yeah. So when I was talking about the catch up, I was really describing something more like what folks would encounter in, like a master's of data science or something, or even increasingly there's even like bachelor's degrees in that. But I think what you're referring to, if I'm correct, is more like the kind of amazing work that postdocs do and the graduate students that present papers at like KDD and things like that. Oh yeah, it's absolutely critical, because let's face it, if anybody's going to try to implement something, they're on a steady diet of these academic papers and these white papers. Yeah. No. I think those are two different, very different distinctions in what little experience I have with trying to crack the code on this in higher ed is with folks much earlier in their careers than the kind of folks that you're describing.
But I think you brought up a really good point, and like it's kind of a cliche to mention Malcolm Gladwell in this context, but he has this 10,000 hour rule that he based his literary career on. And it's true also in data labeling, and it's true in the fact that the human brain is a remarkable classifier. And you ever seen those TV shows in which people have to guess music tracks? We had them in Italy when I was growing up, and the music track plays, and within a split second, someone can guess what track it is. Tens of thousands. That is just the human brain becoming a really good sound classifier. And that goes similarly to any other field. And you have to be a medical doctor to understand a disease, but you don't have to be a medical doctor to identify a caries in a tooth if you've seen 100,000 teeth before, at least not conclusively. And the distinction there is that it takes a whole lot of diverse education to understand the intricacies of an expert-led field. Medical is probably the most extreme, but let's talk about manufacturing defects, for example. It takes like the sound of the object if it has a crack in it, the temperature that may lead to the cracking in, say, fiberglass. But if you are a human labeler and you've never seen the fiberglass creation of a boat before, and you've seen 10,000 defects on a screen as part of your labeling training program, the 10,001 you will be pretty much an expert in identifying. So with the right tools and with the right diligence in understanding the QA process of a human, you can actually create a whole lot of great training data without necessarily only relying on domain experts for everything. Another thing we see increasingly popular is we have a workflow system on V7 that allows you to combine different cohorts of people in a sequence or in parallel. And you tend to have like the average human labeler at first, and then tendentially you start with a model, then a human labeler, then an expert labeler to do the final review.
Yeah, as I was listening to you, I was thinking that, it's not that one expertise is better than the other. They're just very different. I think even at the most fundamental level of perceiving what they're looking at or what they would define as anomalous, there are probably some differences there. I know I've done mostly traditional machine learning in my career, but I know that, even among my colleagues, I'm usually very stubborn about something. I usually, like, if I'm working in manufacturing, let's say, I want to talk to the folks on the factory floor. And some of my folks, even my friends will say, Keith, we've got, these data dictionaries and we've got the metadata and we have the person who runs the factory floor here. Why do you want to talk to the folks down by the machines? But I find that if I talk to them about data, they tell me a different aspect of it than I get from senior management. It seems that there's something similar going on there, that there's literally at the level of perception, there's things are perceived differently.
Yeah, precisely. And we sometimes see corrections being made at the labeler level that flow back to the experts. That's not an uncommon thing, because sometimes the expert is an expert in the theoretical side of the field, but not in the various permutation of a class in a data set. So class drift of, say, even taxonomical stuff, complex plant biology for the teams that are trying to classify the intricacies of life in plants and the way they evolve in a disease that may affect plants and crops in agriculture. You tend to see sometimes the labelers starting to not necessarily outclass the experts, but they bring forward a different perspective, especially in the concept of class drift or ambiguity. We speak in human language, and we like math, so we classify things into buckets, but there is no such thing as discrete classification in most biological fields. So a lot of things are blended in between. Same thing would go for a defect. At what point something is a defect and isn't? What is the distinct line? It's always a blur. That's one of the things where they tend to identify things the best.
Well, you've put your finger on something that's been mentioned before in conversations about this, and that's trying to make sure that there's some way to have feedback. Naturally, the subject matter experts might be part of the prototyping and training for the annotators and labelers, but having feedback potentially go the other way, where the labelers and annotators discover things that you want to inform the subject matter experts about, right? So it gets me thinking about a related subject, and that's workflow. How do you, it sounds like these two different kinds of expertise, obviously both are important. So in terms of the life cycle, in terms of the machine learning life cycle, where do they play their most important roles, and how do you get good communication back and forth between them?
You see modern AI companies, so to speak, they have these two phases. They have the R&D phase, and then they have a production phase. And they're not necessarily too discrete. Sometimes the production phase has another R&D phase in parallel, because R&D in a field where performance doubles so quickly never really stops. We're going to have a fair few years of people throwing away everything and retraining models from scratch and all. And in the R&D phase, it's a lot of labeling, very little training, and very little data selection. We're basically throwing the kitchen sink at the model. In the production phase, we have an idea of what the model does and where it does well and where it does poorly, and we're able to feed back, by we, I just say in theory, data scientists around the world. They feed back the data from their model in classes that performed poorly or scenarios that were unexpected back into the training data platform, so back into V7, which goes into a work stream or a workflow. And in that workflow, humans will look at the data, assess it, and then correct, basically by retraining if you will. Retraining is a misnomer because it's not going through a GPU, it's going through a human, but you're effectively changing the training data so that the AI improves itself. And I think this new workflow system that is more data-centric is, in a way, going to also change the way we see the concept of training AI, where today you train a model by, if you're in the industry, if you're a data scientist, you know that you train a model discretely, it starts to train, you wait a day or so, and it's complete, and then you can put it in production. But I think most layman people assume that machine learning is just continually learning all the time and continually adding weights to itself like you would in continual learning. And that's not the case. But with labeling and humans in the loop, this kind of production phase AI, I think that's a reality that we can create. So one of the most exciting things, I think, is continual learning plus human in the loop. It has practical limitations, but we can get very close to it with how cheap GPU usage is today, by doing continuous iterative model training. And there's fantastic tools out there for tracking experiments that a lot of teams use. And then on the training data side, iterative improvements of the training data by humans. And the combination of the two, I think, is the most competitive thing you can do in creating very strong models.
I have a theory about why folks get confused about that. Just kind of a general audience confusion. I think that they may be hearing about some of the stuff related to to games like Arthur Samuel's checkers or chess or AlphaGo. And they get the impression that, as you point out, it's always learning, and you go on your lunch break, you come back an hour later, and it's even smarter than it was when you left. Do you think that could be the mental image that some folks have?
It makes sense, right? Because that's how we work as humans. We're continuously learning, and then the way we actually learn about an object in 3D is we imagine it's behind. If you look at a car, you imagine that it has another side to it. And then you can verify with your own eyes by walking around it. And then you have this continuous training loop in which you remember that car has an actual backside. A car, we've all seen one, but imagine an object you've never seen before. The dark side of the moon, if you will. Yeah. By looking behind it, you learn it is. And with models, of course, it's not the case. You're doing inference or you're doing training. Really, are we doing it at the same time? We have a bit of the shadow of classical machine learning that affects that, because with structured data machine learning, you can train on the fly, basically in real time. With image and video stuff, you can, but it's not going to be the stuff that performs really well. But I think we're getting there. I think that's the experience that people want. So there's a lot of consumer applications where people want to feel like something is training, is learning from you as you use it without any interruptions. There's ways of simulating that. Like Apple notoriously does it fantastically with the keyboard that you have on iOS, which learns predicted typing from what you type.
So to help people picture what it's really like, if it's not continuous improvement, getting better even when the data scientist is sleeping, kind of a thing, help everybody picture a little bit more what it's like. I mean, you were describing it just a few moments ago, but basically what's happening is it's more like you're doing a new batch. You identify flaws in the model. You have to find out how to correct for those flaws. That step almost always involves humans to develop more training data, perhaps training data that's weighted on the kind of data where the mistakes are occurring. Then you go and you rebuild and redeploy. That was off the top of my head, but is that kind of the mental image that probably folks should have instead?
I think if someone is a listener here and they're relatively new to the difference between deep learning or machine learning in general and traditional machine learning, is that imagine that your brain and all of your memories are VHS tapes that are uncompressed, and your brain is the compressed version of that. So you actually don't quite remember, let's say, your first grade school play. You remember glimpses of it that are compressed. If you were to see it again, you'd be like, yeah, I was there. So there's a compressed version of all of your knowledge inside your head. And imagine there's an uncompressed version somewhere in a library in VHS tapes that take a while to read and watch. That would be swell if that existed. Unfortunately, as biological beings, we don't have that privilege, but with AI, we do. And that's the training data platform comparison. You have this library of all of its knowledge, and you can actually open the VHS and scan it. Imagine you have VHS reading eyes, magical VHS reading eyes. For those who are younger than that, even so, it's like those old cassettes, DVDs on a tape. And you're looking at it, and you basically get to see the actual training data and what you experience to compress that information into the weights inside your brain. Nowadays, you have companies and academic groups that are creating enormous libraries to try and compress the entire internet, the entire English language, the entire driving experience of tens of thousands of drivers, or the one I'm most excited about, the entire medical knowledge of the world's best doctors, so that you can create AI models that can serve everyone in the world who would never have access to these best doctors in the world. So you're creating this gigantic VHS tape library, and every now and then you have to roll out all of the tapes, throw them into a big old training machine that then creates a brain, which is compressed at this point. And that's your neural net, that's your model. How do you actually know that the thing works? You show it VHS tapes as it learns, and you see whether it guesses things correctly or not. That's another topic that's becoming ever more important. A lot of your knowledge, your network's model is bound to the architecture, but a lot of it is bound to the quality of the training data you present to it, ever more importantly. And to actually, one of the best returns on investment you can have is to actually fix any bias that this thing has, or any bad knowledge, like it knows an incorrect fact, is to actually go and look at the experience, the single tape that caused that, and fixing it in retrospectively. Maybe if it's a driving AI, you've identified a stroller as an obstacle you can drive over. And so this thing has a little bit of bias towards driving over baby strollers. And you obviously don't want that. So how do you go and find that bad case and then fixing it?
Well, or an example that I saw once that just really somehow struck me as an interesting one is you might have an autonomous vehicle that's pretty good at detecting deer running across the street. But when it encounters a kangaroo, which doesn't really move like a deer, it has a heck of a time, right? So then again, you go through that step, and the next thing you know, you probably during that iteration step, you need some humans labeling kangaroo data because you didn't have enough of it, right? And unless the company was founded in Australia, in which case they might have the reverse. They might have the reverse problem, right? Yeah. So very interesting. But I think that iteration, I think, isn't clear. It sometimes in the press comes off like magic, and it's really not magic. It's a lot of a lot of hard work by a lot of different skill sets. I want to start moving into some specific industries, and what is one of the reasons that I've been so excited for today is that you've got this front row seat in your role at V7. Not really for just one industry, but a bunch of industries, because you have very diverse clients that use the platform, as do we in what we do. So regarding medical AI, could you comment a little bit about HIPAA and data privacy? Because if you've got these annotation tools, you've got humans that are doing annotation and so on. I know this is a big topic, but could you talk just a little bit about security and privacy and HIPAA and medical?
Huge. And, ever more training data is kind of the competitive advantage of some of these companies doing medical image analysis. So one thing that we make very clear is where the data is stored for the customer. We have this special type of integration where we can have the users read data directly from the end client's own storage bucket. That means that if the client, for example, needs board certified radiologists to do the labeling of certain data, the data needs to be stored within the United States, and we don't get in the way of having to store it where our standard storage is, which is in Ireland for GDPR compliance in the EU. There's also a lot of controls that we've put into place. So HIPAA and also FDA, that's another really big one, because a lot of models that do actual diagnostics will have to go through FDA approval. We're kind of priority from day zero for V7. We saw this niche that was untouched mostly in the labeling of medical data, and autonomous driving at the time was really spearheading the quantity of data processed for AI, because there was the race towards level, at the time was level 1 autonomous driving, anything you could get to at least drive on the highway. And now there's an equal race happening in medical, and you need to build things from the ground up to support that. So one of them is HIPAA compliance. The data is stored at transfer, at rest, all the various rules, and then FDA compliance. Every annotation has an author, and that author is known and persisted throughout. We have logs of every single label that's being made, because those are clinical decisions in some cases. So you're saying, like, this person has a tumor right over here. And we also have these this type of both version control. Every time you export a data set, you create a version of that data set that corresponds to probably the model you want to train. So some people have you do hundreds of experiments, so they have hundreds of model versions. Without this tumor class, with this tumor class, without this patient group that is an outlier, with this patient group, but to be used to test on another patient group that is of a different ethnic background. So, tumor detection might work differently. This is extremely common. And then finally, on the labeler side, how do you get people from across the world to look at sometimes medical data and then privately label it in a way that's secure? We have controls for disallowing people to download images, export any of the information. The platform can be used directly from a web browser, but on a web browser, you can also create controls to prevent, for example, taking screenshots of things, and you can pre-anonymize the data if it's medical things and DICOM data by just not reading the header.
You've touched upon some things that I want to follow up on, because it's related to our next question. So we've been kind of dancing around this a little bit, because we talked about having enough images of deer but not enough of kangaroos, and then you mentioned tumors, not just tumors in general, but of a particular class. So if folks are new to this kind of thing, how do they get their head around how much data they need, how diverse that data has to be, and then getting right down to the nitty-gritty of it, like how many they need of a particular class? Like if they did have a car that got exported to Australia and there was a collision with a kangaroo, let's say, how do they know how many kangaroo images now they have? They might have thousands of hours of footage, but they don't have that. So whether it be tumors or these various things, how do you know that you have enough data overall and enough in each class?
I'm thinking in my head how to make a comparison to real life and how humans learn things, but it's particularly hard because the question has the ugly answer of it depends. But to try to put it into as secure as like actual terms as possible, it used to be that in the 2015 era for a classifier, if you didn't have 1,000 examples of something, you're wasting your time. Then we started to have fewer shot models because we realized that a lot of the weights needed inside a neural net can be just pre-trained by just shoving ImageNet in it, or other enormous data sets with a lot of just general images of tapirs and church abbeys and whatnot. And then you basically build the necessary pre-knowledge of a model to actually figure out the actual nomenclature and taxonomy of the world. In practical terms, on V7, you need a minimum of 100 objects to train a model. It won't do fantastically though. It will do well if your domain is narrow. So in we find that some people in manufacturing will be getting stellar results with 500 examples of, say, a mug that has a crack on it. But in detecting roadkill, the variety of roadkill is extremely diverse. They're not only in animals, but in angles and in the appearance of it. Could be.
Yeah.
So think of the world. Think of the similarity of images as a bell curve. If your bell curve is very narrow, you're not going to need a lot of examples, unless your classes, so the with or without what you're looking for, are extremely similar. In that case, it's a little harder to check. If your distribution is very wide, which is the world around us, for example, or autonomous driving, which has extremely wide varieties, not just in climate appearances, but also the way the road looks, the way vehicles look, then you have a much bigger challenge because you need millions of images to actually reliably do something that will be safe enough to put your own body inside of it.
That makes a lot of sense, and as obvious it is, listening to you say it, that variance is an important component in this. I don't hear people talking about that very often, but if I'm the company that makes our beautiful CloudFactory mug here, and this is the only mug we make, and it's only in this color. Unlikely, right? But let's just run with that for a second. And all I'm trying to do is detect whether or not this one mug in this one color has a crack in it. Then a couple hundred cases might do the job. But I'm guessing that medical AI doesn't meet those criteria at all, because the kind of information that you would see in medical imaging probably is incredibly diverse in terms of how it manifests itself, or the kinds of things that could be confused with that symptom and so on, right? So that's where you get into the hundreds of thousands or millions, right?
I want one of those mugs, by the way.
I'm sure that can be arranged.
I think there's also another problem that is very prevalent, especially medical, which is the biasing factors of training data. And let's say that you're just running a classifier for chest x-rays. A lot of the learning will happen in the patient notes on the top left and top right of the x-ray, where it says if it's supine or if it's male or whatnot, rather than actually looking at the organs. So AI likes to cheat and likes to find the shortest way possible to actually guess something correctly or incorrectly. So classic example, I think one of the first DARPA projects in computer vision was getting computer scientists to create a system that could identify tanks or airplanes. Yeah, you know the story.
I know. I'm smiling, but I don't think everybody's heard it. But it's a classic, and if people haven't heard it, they need to. Yeah. So
yeah, basically, the best way to identify that something is a tank and something is an airplane is not to learn any of the objects at all, but look for the most prevalent color in the image, and airplanes is going to be blue. So if you put a tank in the sky, that classifier would say, oh, that's an airplane, of course. The intricacies of like what what does it mean for it to be a tank are, I think, roughly grossly underestimated by us humans, which selfishly think like, oh yeah, of course, it's going to figure out that it's a tank because it's a tank in the air. Of course, we've all seen a tank before. But that's not the case. You actually need an enormous amount of data. And when you're born as a baby, you actually already have some intrinsic knowledge inside of your brain already. So it's not even fair to make a comparison with how children learn. But, ask any 5-year-old how many things they've learned every day, and it's probably going to be a whole lot.
Yeah. No, that's a random memory you're causing me to have. When I was in my late teens and in basic training, we used to get, I think it was like playing cards or something, but it had all these tanks on them, and I don't know about my peers at the time whether or not they were able to process this information, but it was almost impossible to tell these tanks apart, down to the individual nomenclature. So I can totally imagine that an AI model might say, "Oh gosh, it's it's an American tank or a Russian tank or what have you, because it's got Cyrillic, written on the outside." Which, if you're 500 meters away, isn't going to help you, because you're not going to be able to see that. You have to go based on shape. Yeah. So anyway. We digress, but I can see how this is challenging. And again, humans get involved, because if you discover that your data is out of balance and it's only making the prediction based on the background, or like the other classic one, which I'm sure you've heard of, is, a dog versus wolf, and the wolf pictures are always in the snow, that kind of a thing, right? That if you discover that kind of a shortcoming, you have to then boost up the number of cases in this rare category, of maybe the wolves that don't have a snow background. And again, you could have this elaborate iteration that almost certainly has humans involved to improve the size and the completeness of the data set. So two more things I want to talk about before we get to a Q&A, but I want to alert folks to the fact that I haven't scrolled down to, oh yeah, it looks like we already have some Q&A activity going on. So we will be transitioning to that, everybody, in about 5 or 8 minutes. So keep those questions coming. So next one, we've been talking about images and how challenging that can be. So get ready, Alberto. Now we're going to talk about video. Drones, of course, generate a lot of video. And now you were talking about, roadkill. You had an angle and all kinds of different things. So now you actually have the camera itself changing perspective, changing altitude, changing angle of approach, and so on. So what's kind of the state of the art in video? This drone-based video, what are some of the use cases you've seen, and what are some of the new challenges that you see in video that you don't encounter necessarily in images, as difficult as images are?
Yeah, we process a lot more video than we do images, of course, because video is made of tons of images, realistically. And it's becoming an increasingly preferred method of creating training data because you have temporal evidence. You can create embodied intelligence to understand if something goes behind the wall, it doesn't truly disappear, it's just behind the wall. And it's great for test sets. You can take a sample of images and then test it on a video, and you'd be surprised if you've ever seen AI run in real time, how different the results between frame 1 and frame 3 can be. And sometimes you have correct identification on frame 1, 2, and then in 3, you don't have enough confidence because of some small amount of light that's coming through, or the angle is just a little bit too different. So we are seeing video definitely a lot in drone imagery, aerial imagery. Drones becoming now such a harder commodity means that there's a lot of entrepreneurs that have been able to create all kinds of inspection systems for bridges, for infrastructure, for roadways, for crops. And that's really cool, I think, because they're happening all over the world. And these are also markets where you can start small and then really make a lot of impact using commodity hardware and then developing something using AI, using the tools available like V7, like CloudFactory's workforce. Where we're also seeing a lot of videos is obviously autonomous driving continues to be an enormous behemoth in the field, but there's new areas of videos that are emerging. Last year was really big on surgical video, taking a big splash in medical, because surgeries are generally monitored by endoscopes, and there's a lot that can happen. And for a hospital to know how every surgery is going in real time, mission control style, is enormous amount of saving, because every surgical room is a huge cost. Where else? We're seeing animal and cattle monitoring, and we're seeing, again, traffic video, stuff that's happening inside cities, or retail with autonomous checkout attempts, and the newly opening stores that are doing this AI-based checkout for just walking out without needing to pass through self-checkout system.
I'm gonna make a little bit of a mental leap based on a number of comments that you've made. When we were talking about images a few moments ago, you were saying that the taller and skinnier the bell curve is, the less variance you have, you can get away with smaller sample size. So video, by its very nature, is this huge data set, right? So do you find that those that are most successful in video tend to be somewhat niche, like only do endoscope, video and so on, to try to reduce the amount of diversity in the video data so they can build effective models, since they already have all these challenges like changing in lighting or changing an angle or what have you?
Yeah, something that we see commonly, and that's something that we kind of help on the tech side, is being able to create you upload a video that is 2 hours long, and then you sample frames every 10 seconds. So if you load a video on V7, you can keep the video as an integral piece of training data, but you can do the labeling only every 10 seconds as almost a new image. And another thing that we do is we interpolate the shapes in between these labeled frames. So in polygons, for example, you might have my hand like this, and if I am rotating it like this, you want the data in between to also be labeled. And you can interpolate that data using, again, AI models that can do this very well. Yeah. But it does present a bigger challenge, but I feel like if you can film something video-wise, it means that by default it's embodied in the world. And it means that it's you just have to deal with the fact that the reality we're in is complex, and AI is an attempt at compressing it. And it's never going to be a perfect modeling. Otherwise, we'd have to recreate the universe in a bottle. And we don't have time for that yet.
Yeah, so it tends to be, these successful applications tend to be really quite focused and specific, for all the reasons that we've been talking about. Okay, new topic, but our final new topic before we switch over to questions, because actually we have about 20 minutes to go here. So Jan LeCun, a name that you'd be familiar with, of course, he was working on OCR, character recognition stuff, like late 80s or something like that. So I know that recently you and I were talking about OCR and how there's actually considerable challenges still to be overcome. But when people talk about a technology that's been around for more than 30 years, not quite 40 yet, but maybe, I don't know, if we looked up the earliest applications of it, it could be somewhere approaching 40. It would seem like solved technology, but there's actually some ongoing challenges there. Could you comment?
We've seen OCR for so long that a lot of people who are entrenched in the industry of document processing thinks it's a solved problem. And currently, most OCR tools that are implemented, most of the automatic document scanning that you're seeing is 50% accurate or less.
Wow.
And the reason is that a lot of it is just using classical ML, and it works for easy data sets. It works for your perfectly printed page where it's in Times New Roman and an A4. But if you have any handwritten characters, it's still not perfect using classical ML. But deep learning approaches that are coming out, and there's, if you want to try one that's really good, knock on our door. You can have V7's text scanner do it for you, and CloudFactory to verify and label the actual fields of interest that are interesting to you. That can get you to 99 to 100% accuracy. And we have seen a lot of growth in that field because there is a shift happening in the document processing world, and anything that relates to seeing a piece of paper and scanning it, where there's a shift away from this classical ML set of tools into deep learning approaches, and the gains are huge. So it's definitely not a solved approach. There are also academic conferences that try to read text that is rotated on shop signs, that is in fancy fonts, and that is a never-ending challenge, almost. But it's starting to become really, really good. Something that
I imagine drones. Drones are going to have to be able to read street signs, but at different speeds or at different angles, and I imagine that's probably not as difficult as handwritten. But what are some of the things that you find still have to be routed to humans? I think you mentioned to me at one point something is seemingly straightforward as medicine bottles. Have some things where the characters can be read, but sometimes the context requires a human. Where do you find? You were describing the partnership between the deep learning doing OCR, but then sometimes being routed to a human labeler. Where do you find the technology needs a helping hand?
If you're doing computer vision, I think every piece of training data that you use in production, realistically, should be checked by a human. If you're only relying on model-assisted labeling solely, you probably are missing out on efficiency gains that would not cost you as much as the pain of having to fix them later. But increasingly, you can combine different models to get as little work to the humans as possible, and that work to the humans becomes ever more crucial, because then they're picking out the stuff where your AI really fails at and really needs to start learning about. So realistically, I think but in terms of the ones that needed the most, all medical cases, all cases where people's lives could be in danger, like autonomous driving, all cases that manipulate things in the real world, such as robotic picking, and all cases where a decision needs to be made that ultimately has an impact on a real human being. KYC, that's things like ID processing for when you're registering for a new bank. People don't want to wait for days to get that process. So you want to make sure that your AI is accurate for that. Anything related to document processing where it has a real impact, the subtotal of an invoice that has been processed. You don't want to charge someone for the wrong amount of money. It creates a huge amount of pain.
But actually, I was going to follow up, but we have some really cool questions that I want to make sure that we get to as many as we can. So Shimalik asked, and Shimalik, I hope I pronounced your name reasonably well. He's actually asked a question on our website where we're monitoring questions. And here it is. I'm just going to throw it out at you, Alberto, see what you think. Can you please elaborate on what kind or specific tools can be used for continuous learning?
There's not a lot of tools that are publicly released for what an academic would call continual learning. In fact, continual learning is still considered an R&D sector of deep learning. Nonetheless, you can still get very close to continual learning by either training models on a platform like V7, where you can train them in one click, or also combine experimentation tools like weights and biases and test out what parameters work best for you. And then every time you have new data for your data sets, just start a new training session and then get a new version of that model. The actual continual stuff where it learns basically on the fly, I wouldn't have any good recommendations to do, but if anyone else in chat knows, feel free to drop a line.
Well, but I appreciate that we've revisited that topic, because that for me was one of the really big insights of our time together today, which was that what's more the reality of the situation at the moment is you identify that there's a shortcoming in the model. You have to go not all the way back to ground zero in R&D, but you have to supplement the model by increasing certain cases in the data, which means basically you're going back to creating more training data, but of a particular kind. And that's almost certainly going to involve humans once more, and then you circle back. So it's iterations and deploying in a new batch, like a version 2.1 or 2.2 of your model, or what have you. Mike Worley on LinkedIn had a follow-up question on the kangaroo case data. I'm going to throw this out to you. I'm not. He simply says, use case for, would the kangaroo instance be a use case for synthetic?
I don't think so, because synthetic data has a big flaw. It's good for testing. It's not good for training, because what synthetic data is, you have a CAD model of an object. All you're going to learn is that object and the possible varieties that the rendering engine that you have will compel. The rendering engine is hand-coded by a human being with 10 digits, an ape effectively. So it will never be as complex as a video in the real world. And the alterations that the natural world can create in that appearance of a splattered kangaroo run over by an Australian big rig. Yeah. So unfortunately not. You would have to model a lot of splattered kangaroos, and it will be probably more worth your time to just have a drive in the bush and film them.
Yeah. So actually, to actually go and get some actual kangaroo data. I'm trying not to imagine what you're describing, Alberto, because I've been face to face with kangaroos before, and they're very large animals. Yeah. Anyway, they're human height or taller. But anyway, I'm just trying to imagine that and trying not to imagine. Anyway, so Ronald asked a question on Drift. Actually, I didn't know that we were on that platform. Not familiar with Drift. I don't know if you can see this question. It's a little bit longer than some of the others, Alberto. We've developed KGE, meta-knowledge, aggregate of associated weighted themes and concepts from a collection of documents. Can metacognition be done here?
I don't know. Sorry, I don't. It's not a topic I'm too informed about. So my apologies, Ronald. I don't have an answer to your question.
That this encourages me to, or makes me think to mention as well that I hope the conversation continues beyond today, because certainly I'm very curious, Ronald, to know a little bit more about what you had in mind, and that's the kind of question that perhaps would take place on LinkedIn after after the event, to do a follow-up.
Yeah, if anyone else wants to follow up on metacognition, whether Ronald as well in the comments, I'll do a Google of it afterwards.
Shmulik had a second question, and it's a multi-part one. And apologize, everybody, if I'm not making eye contact with the camera and I'm looking over. It's because I'm reading these questions. I think we've all lived online for the last year and know how that goes. So he refers to, how would you analyze your data to understand what types of classes you need? I'm going to suggest, Alberto, that we take just this first part initially, because Robert Monarch, who wrote a book on Human in the Loop, was talking about this a little bit and saying that, you really have to iterate from an early prototype. And each time you're probably increasing the sample size by an order of magnitude. And you were referring to something that sounded very similar to me, where you said, the manufacturing and the crack and the mug kind of thing, you might start with as few as a couple hundred, but you probably wouldn't deploy a model that was built on just a couple hundred. So it seems to me that that's what Shmulik is getting at, is that there's not one answer to how much data you need. It's increasing the data as you go through these iterations. Am I on the right track?
Yeah, exactly. And the easiest thing you can do is check class balance, make sure one class is not over or underrepresented. This is hard if you're doing, it's easy if you're doing classification. It's hard if you do object detection, because you need to count the number of bounding boxes across your whole data set. Some tools, V7, for example, does this. Many of them do not. And you then need to make sure these are balanced. And then I think one of the more effective things is not just check your stats at the end of your training session, but test it on various test sets at the end, of various validation sets. So if you want to train a car that drives everywhere, you want to have a test scenario in the snow, a test scenario with fire trucks, a test scenario. You want to test these independently, like you would in kind of an exam.
But you might, the very first time you're building a model, the now famous mug crack model, right? You might do 200 images with like studio lighting, so that's super uniform, right? So that you don't get the mug and the snow scenario kind of thing. But what I'm saying is you might have images under fairly controlled circumstances when you're building it with just a couple hundred images, to see if you're focusing on the relevant thing, and then deal with mugs going down an assembly line or so on. I'm being somewhat speculative here, but I'm trying to build off your comment about reduced variance and how you might combat that in the early stages of prototyping. There's questions are being added here. I've got to be on top of my time management here. So we may circle back to that multi-part question, but I want to start on Tom's question because it's taken us in a new direction. And Tom asked on LinkedIn, in NLP, you could have high accuracy models, but without proper post-processing, a model could be worthless for a company. Yeah, if you could talk a little bit about, you actually mentioned MLOps, for instance. So that's when we're going to be on our post-deployment period. Could you talk a little bit about model monitoring and maintenance type issues post-deployment?
Yeah, I think making sure that your model feeds back low confidence items and potential errors is kind of every data scientist's priority. Part of a lot of SaaS companies like ourselves creating these tools, and part of your self-providing services, is so that data scientists can focus on that rather than on doing the hard work of creating a training data database. They can actually focus on making the AI better. And then on Tom's point of what's the difference with NLP and its post-processing of the output, in computer vision, the output is also something you might want to interpret. Like the IOU between two bounding boxes can tell you if my hand is actually holding this cup or not. Detect the cup, detect the hand. If they overlap, then it's fine. But I think that uniquely, more uniquely so than from an NLP, Andrew Kirpati has a good analogy on this. Like if a car is parked on top of a parking space, It's easier to classify the car as parked than to detect the car, detect the parking space, and then write some human hand-coded logic to say if the car is on top of the car parking space, but not too much to the left, not too much far to the right, then it's parked. Just let the AI figure it out by showing it more examples. And I think that's one of the cool things about the Software 2.0 example-based training that we're going to. So I think less post-processing might actually be good.
Okay, fair enough. Fair enough. Again, my attention is divided here, but I think what we'll do is we'll let Mike, as a follow-up, get the follow-up question. He's encouraging us to talk about edge cases, maybe going beyond the edge case example of the kangaroo earlier. What about synthetic for scenarios hard to capture with real data? So Mike kind of wanted us to briefly revisit synthetic, and that will be our final question. Actually,
if you can predict them, then yes. For example, if fire trucks might be extremely expensive to hire to train self-driving cars, so you could create 3D fire trucks. They all look relatively similar because you know what a fire truck looks like. If it's a defect, of course, then the answer is definitely not. Do not try and 3D model something that looks natural and happens due to entropy, like a defect, like a rubble or something that we see, as, for example, waste. It's not something you want to create synthetic data for. So it really depends. If it's human manufacturing and predictable, then synthetic data is potentially a viable option. Again, I think it's always best to use it for test sets as opposed to training sets.
Sometimes my brain works in strange ways. I think as a general rule of thumb, what you were saying is that under certain predictable circumstances, you can generate some synthetic signal, but you would try to generate some synthetic noise at your peril because you're not going to be able to predict what it might be like rubble or things like that.
Yeah, exactly. Your brain is not a model of the universe.
Okay. Yeah. All righty. So I've had a fantastic time. I hope that everybody's enjoyed it as well. And I hope this is not the end of the conversation. Again, there are a variety of ways that you can continue to interact with all of us at V7, at CloudFactory, and so on. So first, Alberto, certainly I want to thank you. And one way or another, we're going to hunt down the now famous mug. We'll make sure that it doesn't have a crack in the mug when we send it to you.
We have the same sweater. We might as well have the same mug too.
Yeah, I noticed that we're in the same color today. And I want to thank all of you for joining us. There are a couple of very simple things that you can do to stay in touch. With the holidays approaching, we won't be doing an event like this again until 2022. But I encourage you to follow CloudFactory on LinkedIn. I encourage you to follow V7 on LinkedIn. And that will be a great way to stay up to date on everything that's going on. So I want to thank you all for attending and thank Alberto once more.
Thank you, guys.
And enjoy the holidays, everyone, and be looking for future events down the road. Thanks, everyone.